So welcome to lecture 9. So we are going to derive the formula for longitudinal strain. So in the last class we had a lot of discussion about what could be the definition for longitudinal strain when you have an arbitrary body and undergoing arbitrary deformation. So what we found is that we can think of the infinitesimal or very, let's say, small line elements at any point in the body and think of the change of length of that particular line element. Okay, so this is again the reference configuration, and here on the right is the deformed configuration. All right, now think of a point at big X in the reference configuration and a line element starting from big X and of finite length. Therefore, the tip is big X plus delta big X. Okay, and this is then going to go here. Okay, see, I am just so used to, I just forgot to tell all of you that there are several books where in the reference configuration they denote the letters with capital letter, and in the default configuration they denote the same variable with small letter. Okay, for example, a point here in the reference configuration by capital X and the same point in the deformed configuration by small x. And I am so used to it that I just started doing that. But in this course, just to be consistent with the book, we are denoting reference configuration by a small x, right? And in the deformed configuration, it's by a small y. But there are several books where it is using capital and small letters. Okay, and I also do that. So and let's make it not dx but delta x. You must know the difference between delta and d, isn't it? Delta x is just some length. Delta need not be infinitesimal. It not, I mean, it's not. What I should say, it is not. It is not infinitesimal. Whereas dx is infinitesimal. Infinitesimal. And what is infinitesimal? Simply means as small as you can think of. Really, 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 really tiny. The limit going to zero. Okay. And you can recall that we had derived this delta x was equal to big F. Okay. Today I'm really into my old self. Delta y is equal to big F delta x plus, can you recall that there was an error term? Okay, and same thing in case of, if you do it using infinitesimal line elements, then it is dy is equal to big F dx. Okay, what is the difference between these two? Of course, the first one has got some error term also, and the second one is exact. As far as lines are concerned, what is the difference between delta x and dx? So delta x, the line delta x, as you can see, is not at point x. It is emanating from point x, right? But it is not at point x. It's in some, in a small region around point x. That delta x is line. But dx, although it's a line, and there is a difference between line and a point, but it's an infinitesimal line of zero length. So it is at point x, starting from point x, getting over at point x, and it has also some direction. Okay, so that's the difference between the two. So today we are going to define, or we are going to derive the formula for the longitudinal strain for these line elements. Okay, and it is instructive to start with this delta x, and you'll see why. It will give us a lot of interesting information. So if you want to think of delta x, then we have to use this particular map, isn't it? So what is the final length of this line element delta x? If I ask you the original length, what is the original length? So that's delta x dot with delta x itself, isn't it? And this you can say is, let us say, big L square. And if I ask you the deformed length, then you would say delta y dot with delta y, isn't it? And that we would say is a small L square. So let's now find out this small L square in terms of original length. Okay, or try to use this deformation gradient in here. So again, this is small L square is delta y dot delta y, and use the formula for delta y from above. So we have big F delta x plus big O delta x whole square. I hope that all of you are aware about this big O notation till now. Anybody not aware of this big O notation? Anyone? Okay, if you are aware, that means you are very well prepared for the quiz tomorrow then. You will have questions on this. All right, now what do I do? How do I take the dot product? So of course you cross multiply. There are two terms on both the sides of dot product. So one of the things that you will get is f delta x dot with f delta x. Okay, and remember that it is this thing dotted with this thing. The bracket is important. Okay, then what else have you got here? Anybody, can you tell me what would be the extra thing? This is to be dotted, then this is to be dotted, and these are also to be dotted. The three pairs have to be dotted. So somebody has written its order of delta x cube, Avinash, which is correct, of course. If you understand the meaning of order, then you can appreciate it. For example, look at this dot product. One of them is of the order delta x square, and the second one is of the order delta x. Then obviously if you multiply the two, you'll get of the order of delta x cube, isn't it? So instead of explicitly writing the formula, you can simply say big O delta x cube. But you see the last one, this thing, order delta x square into order delta x square, that's big O delta x 4, isn't it? But when you say big O delta x cube, it also contains all the other orders of more than 3. So it contains order 4, order 5, order 6, order 7, all of them. That's the beauty of the definition of this big O. So what you highlight inside big O is the leading order term. Okay? So delta x cube is the leading order term. That does not mean it does not contain delta x 4 or delta x power 5. It can contain all of them also. What you have to highlight there is the leading order term there. Okay, so that's why all the remaining three dot products can be combinedly written as big O delta x cube. Okay, so I'll just mention that it is supposed to, or not supposed to, it actually does, shows the leading order term. Okay, all right, so now what can we do? Well, there are so many ways to proceed further. Either you write this as, you see, what is this? A vector dotted with itself. So that's the magnitude of the vector. So you can write it as big F delta x vector whole square. Okay? Or you can also write it as, let me write this and see whether you're following this. I can bring this F on the other side of the dot product and it becomes a transpose. Have you guys seen this identity? And then the bracket is really important. Okay, if you have seen this, then of course you are very well prepared for the quiz tomorrow. So, this is very much like, suppose you have A into a second order tensor A multiplied by a vector A, and I'm dotting with another vector B. Then using the definition of transpose, when you bring this A on the other side, it automatically becomes a transpose, a second order tensor. Right. Very good, Ritvik. And therefore it becomes A dot A transpose B. Okay, so you can write both the two things. So having found out, and okay, you have to remember that we have this big O also missing. So I have to add that. So this is plus big O delta x cube, and same thing goes here also. All right, so now suppose I denote the stretch by deformed length by original length. Okay, so the stretch, I denote it by lambda, which is deformed length over the original length. Then can we say that lambda square is small l square over big L square, right? And we have the formula for small l square just up there. Why don't I write it here? So I have F transpose F delta x dot with delta x. See, this bracket is really important. Don't think that you can write it as F transpose F and then delta x dot delta x. So if you do this, this is of course not correct. Why is this not correct? Can anyone say why this is not correct? And that's because you first have to find out the vector within the bracket here first, and then take the dot product of that vector. And if you want to think of it in matrix form, if you want to think of it, you might have thought that matrix multiplication is associative, so it doesn't matter in what where I put the bracket. You might think like that, but I mean you're right. But let me show you why that is not working here. So I just show you that side calculation. So what you have here is F transpose F delta x dot with delta x. But you remember A dot B, how did you write it? Take the transpose of first one and then multiply with B. You remember? For the dot product, for the tensor product, you have to take the transpose of second one. But for the dot product, you have to take the transpose of first one. So that means find out the matrix form of the first vector and take its transpose and then multiply with the matrix form of the second vector. Now things are all matrices, but you see that the first one you have a transpose. When you have the transpose, you bring the transpose inside, everything gets in the reverse order. Remember? That's how you can bring the transpose inside. So this will become then delta x transpose, then F transpose, and then F transpose transpose, which is F. And then your delta x. So you can see that the two delta x are on the extreme side. They are nowhere close to be multiplied together. And of course here, because, and also you see it's very consistent multiplication. The first one is delta x transpose. So what is the order? Can someone tell me what is the order of this matrix in terms of number? 1 by 3, 3 by 1, 3 by 3. What is this? Anyone? 1. No, how many rows, how many columns? Yeah. So Krishna says 1 into 3, 1 into 3. Okay. That's true. It is 1 by 3. Just delta x is 3 by 1, right? Delta x, the matrix form, it's a column. Delta x transpose, it's a row. So it's 1 by 3. The second one is 3 by 3. This is 3 by 3. This is 3 by 1. And you can see it's a consistent multiplication. And it doesn't matter which one you multiply first, which means you can put the bracket anywhere. But you see the sequence, it has to be in this particular sequence. And then you can put the bracket anywhere. But if you had thought of, no, let me start with the original problem. This F transpose F, and I say, see, this was actually this, no? But if somebody mistakenly writes it as F transpose F into delta x dot delta x, because you thought, oh, what's wrong? I'm just simply doing the dot product, and it's it doesn't matter where I put the bracket, because as long as you have the sequence in the same way, it doesn't matter where I put the bracket. If you think that way, now work this out, and you will see that you have made a mistake. So when you write it in the, it is indeed a mistake, isn't it? It's, you're not getting what you have up here. The two delta x are on the extreme side, you saw, see here. Okay, so this is of course not correct. And as Karthik said, in the second calculation, what you're getting is a tensor, second order tensor, not a scalar. Same with Muhammad Anas also. Okay, so it is very important to know the, the, for example, over here, which is to be dotted with what. It's very important. Anyway, so that was the lesson. So coming back to our formula, so we have this thing plus big O delta x square, all right, divided by big L square, and big L is simply delta x dot with delta x, right? Okay, now what? So Christian says delta x cube. Where is delta? Yeah, yeah, right. Thank you. This is delta x cube. Okay. So I'll make it. I'll write it in a slightly different form now. Now the denominator I can write it as mod of delta x squared, and then I'll do one more interesting thing. So it is same as big F transpose big F delta x. What do you think? Can I do that? Plus big O, and what goes here? What is the leading order term now? What will be the exponent here? Well, let me write this as it is and then just explain to you what I have done. See, you had this delta x square on the denominator, and there are two of them, so, and they are scalars, right? Mod of delta x. Scalars. Scalars you can send anywhere in the expression. Remember that. Scalars you can send anywhere, you can take out to anywhere, it's perfectly fine. But when it is vectors and tensors, you cannot play with their sequence. They have to be in the same sequence as written. What I mean is, when you see here, it is F transpose F delta X. You can't write it as delta X F transpose F or FF transpose delta X. When you have a matrix multiplied by another matrix, let us say A into B, you can't write it as B into A, no? So sequence is very important. But if it's a scalar, you can move the scalar anywhere. So that's what I have done here. So in the denominator you had magnitude square. So one magnitude I shifted it here, right? And the other magnitude I slid it inside the other delta x. And it is perfectly fine because they are scalars. You can move them wherever you want. And if further required, you can also take it out. So, and then you see the other big O term. So Rahman is just writing 0. Why is that 0? So many zeros. So other big O term, I have just written mod delta x or delta x to the power 1 because earlier it was delta x to the power 3 and it gets divided by delta x to the power square, and what is left turned to the power 1. Okay, I hope that is okay with all of you. So, but what is now this thing delta x by mod of delta x? What do you think? What is this thing now? So this is certainly the direction of the line element, isn't it? So that's the direction of the line element. If you go up, so I would say that the direction is n. So I'll say it is directed along n. Okay, it's not unit surface normal. I don't know why you're thinking of surface normal. It's unit vector of delta x. That is true. or if you write it, or if you say that it's directed along n, then you can say that this delta x is n times mod of delta x, right? Magnitude being mod of delta x and the direction being n. Okay, unit vector, of course. So it's the direction of line element. All right. So you can see that somebody was asking me in the last class, will the formula of longitudinal strain also contain the direction of line element, as we were thinking? So you can see it is already coming up, right? So what we have finally is that the stretch square is F transpose F into N dot with N plus big O delta X. So what is this formula telling us? This formula is telling us the stretch square of a line element at X, right? It is the stretch square of a line element at X and directed along N. But it is still, will you say that it is the local value of, I mean, so this stretch corresponds to which point in the body? If I ask you that question now, the stretch formula that we just found out, it corresponds to which point in the body? To point X or to point X plus delta X of the body? Which point? So Krishan says it corresponds to point X of the body. Why not to point X plus delta X? So Saurabh Gita says this is not for a single point. So that's true. So we have found the stretch for a line element, and this was a finite line element which does not correspond to a single point X. It is a line element itself, and as Saikat says, to this neighborhood of X, it corresponds to the neighborhood of X. But we want to derive the formula of strains corresponding to points, local points in the body. Just like you may have seen from your undergraduate class, you have stress at every point in the body. I mean, at each point you have stress. So strain also, when we started, we thought no that we can have strain then varying in the body, different point having different strain, and even at a point in different direction you can have different strain. So, but the formula that we have derived does not correspond to the point X. It corresponds to this neighborhood of point X. So how can I make it correspond to point X? The formula, how can I make it correspond to point X? Anybody? Right now it is corresponding to neighborhood of point X, right? It is not corresponding to the entire body 100%. It is corresponding to a small neighborhood of point X. So why don't I shrink that neighborhood? Right, somebody is already writing here. I'm very glad that you are able to say this. Maybe you have seen this in my video lecture, is it, Saurabh? Or you thought it yourself? So anyway, so you're right, all of you, that why don't I shrink this neighborhood? Let this delta x go to 0. So that's all the idea. If I let this delta x go to 0, then indeed the strain that I will get, the formulas of stretch in this particular case, will correspond to point x, right? To a local point. And of course, the line element then is becoming infinitesimal line element. And then we know that infinitesimal line elements correspond to point itself because they are of zero length. So that's the last thing remaining in this formula, that you take the limit delta x going to 0, and what you have is then simply f transpose f n dot n. Okay, so maybe I'll put it here. Sorry, I think it should go here. And all of you now understand why we have done it, the motivation of taking the limit delta x going to 0. So this gives us this particular formula. You can see that the second term automatically drops out, that big O term. And then if you want to write explicitly, this lambda square is now depending on the point x and also the direction of the infinitesimal line element at x. So if you change x, what is going to change in the formula? Big F. And if you change n, then you already see that n is here. So that's how it depends on both x and n. The stretch square in a body varies from point to point in the body, and also at a point it changes from direction to direction. Okay, so what we have derived is a very interesting formula, but still it is although it looks compact, but we haven't yet seen what exactly does it mean, which we will find out, of course. Any questions so far? Okay, no questions, then very good. Now, see, what was the, what we did is a very, I would say, a slightly difficult way to arrive at this formula. I could have also simply arrived at this by starting with infinitesimal line element. If you had started with, sorry, if you had started with infinitesimal line element, then you would have said dy is equal to big F dx, and therefore L square was dy dot dy, and that would have been f dx dot f dx, which is simply f transpose f dx dot dx, and therefore lambda square would have been small l square by big L square, and that would have simply given you f transpose f, and dx by magnitude of dx, that would have become n dot with n, isn't it? So in a very small step, but then you would have not, sorry, you would not have seen this business of taking the limit going to 0, and you would not have appreciated what exactly we have found out, right? So that's why doing this in a big way or in a difficult way was more informative. So you can see that indeed what you have derived is the formula of stretch at a point. Otherwise, it was of a neighborhood. Okay, so once we have a stretch, we are not done yet. We have to find out the formula for strain, right? Longitudinal strain. So suppose I denote that by epsilon. So because stretch depends on x as well as n, therefore the strain would also depend on them both. So if I denote by epsilon the longitudinal strain, so let us say this says longitudinal strain. So it's a function of x as well as n. Okay, and this is then equal to lambda minus 1, isn't it? That's the longitudinal strain. Stretch minus 1. Lambda greater than 1 means it's a extension, and if it is less than 1, that means it's a compression. So you can then write it as F transpose F into n dot with n minus 1. So that's the formula for longitudinal strain. Okay. Can we relate this with what we have learned in our undergraduate class? Do you remember what was the formula of longitudinal strain in undergraduate class? Anybody? Del U del X, right? Of course, change in length by original length is the basic definition of longitudinal strain. But then the formula in terms of displacement was del U del X, or del V del Y, or del W del Z. Remember? So, is this formula going to give you the formula that you derived in the undergraduate class? See, what you derived in undergraduate class is certainly, it's not like it is of no use. It is of very, it's really of great use. But those formulas were approximate, whereas the formula that you have derived right now is general, is exact. But then, can we derive from here the formulas that we derived in the undergraduate class? So that's the next thing that we want to see. Okay. And before proceeding further, let me emphasize here that this n is the direction of the line element in the reference configuration. Remember that. Okay. So therefore, it is important for you to pick a reference configuration. And also the strain or stretch, it's all being measured relative to the reference configuration. You change a reference configuration, then the strain also changes, right? Because I mean, just here it is change in length by original length. So original length depends on the reference configuration, and change in length depends on both current and the reference. So you must appreciate that strain is not like an absolute thing. So strain is not an absolute thing. It depends on the reference. Okay, just like displacement depends on the reference, and in the formula that we derived, the information of reference configuration is very much there because the n is the direction of the line element in the reference configuration. Just think of, for example, let me give you a practical example. Maybe I can put it here itself. Suppose you have a beam and you put a strain gauge here and the beam bends, okay? It bends like this. And strain gauge can also become curved. Strain gauge would also become curved, slightly curved, but suppose it is almost straight line because it's small strain gauge. Now, when you measure it, the line element direction here is something else, whereas over here it is something else, right? Here it is E3. Sorry, let us say this direction is E1. So here it is E1. But here it is in the deformed, it is not E1. So this N that you see here is the original direction. Okay, the reference, the one in the reference configuration, the original one. Not the one in the current configuration. So I hope that is clear to all of you. And also you see somebody was asking the formula that we have derived, although you are saying it is exact, but is it different than what we practically measure? What would be your answer? Now looking at the strain gauge, what will your answer be? The formula that we have derived, will it match with what strain gauge gives us? Anyone? Can you comment on it? So Rahman says yes. Anybody differing that they will not give the same formula? See, the strain gauge, what it does, it simply measures change in length. So when it measures change, because it's a practical instrument, it's going to measure change in length for a length which is finite in length. Okay, it is going to measure change in length, but the formula that we have derived is for infinitesimal line elements. So obviously that error will be there. So what the strain gauge has given us is does not hold as you take the limit delta x going to 0. So it has some finite magnitude of delta x. Okay, but that's the limitation of the experiment. You can come up with more and more sophisticated strain gauges where the resolution is really really small. So that's what people try to come up with, so that it corresponds more close to this theoretical formula, or so that you can get more local information of strain. Okay, so I think it's already time to say goodbye for today. So in the tomorrow's class, we will try to derive our undergraduate formula of strains from here. Okay, so see you guys tomorrow. I'm still here for some time. You can ask me questions. So Mahadevana says the strain is second order tensor. Can it form more circle on strain transformation? Yeah, it does. Stress is also a second order tensor, and still you have more circle. And stress and strain tensors have so much of similarities. So there is a more circle for strains also.
So,
Yeah.
like, what would be the difference between the Mohr circle we studied in undergraduate and the Mohr circle drawn for this actual strain?
Okay. Um, that's a good question. Um, well, that you'll get to know when we actually come up with the second order strain tensor, and what do its components mean. Only then we can talk about this. See, in the undergraduate class when we did this Mohr circle, we had this strain matrix, and each of the components had some meaning. No, epsilon xx was directly the longitudinal strain. Epsilon yy was also the longitudinal strain. Similarly, you had epsilon xy, which was half of gamma xy. So that was half of shear strain, right? Epsilon xy.
Yes, sir.
So there the components had direct physical meaning. It was either the longitudinal strain or half of shear strain. But in the finite strain matrix that you will see here, the components do not have that exact meaning. Okay,
Yes, sir.
so
Okay,
that's
thank you,
the
sir.
only difference.
Yeah, thank you, sir.
Yeah. So Rajvardhan is asking, how come stress depend on x and n both? If it depends on x, will it not automatically depend on n and vice versa? Well, in this case, it turned out to be that it depends on both. But what if somebody says, no, it only depends on x, but does not depend on direction? That means whatever direction you choose, it's the same stretch. So that's like an example where things are depending on x, but not on direction. But a stretch is, of course, not like that. Okay, so it is not automatic that if it depends on x, then it will also depend on n. It is not automatic. It comes out to be like that for case of stretch. Yeah, so in the last few classes, we have learned to calculate f naught, f0. Yeah, f0 and f are same. I just made it 0 to say that it is constant, but it is the same. F is equal to f0. Okay. We were talking about uniform deformation, so we were restricting ourselves to constant deformation gradient.